So I'll talk first start with what is the square root singularity. I'm sure most of you know, but in the fear of losing some of you as I go forward, I'll just touch upon that. And then uh, I talk about how can we make that singularity disappear. And then most people working in this field have seen something called narrow band chaos. How does it happen? And I'll also touch upon why the Nordmark map doesn't exhibit this. So, to start with, we'll talk about hard impacting systems, which is just a wall. Otherwise, it's a simple harmonic oscillator. As it impacts, it just jumps to the other point. Or we'll talk about the soft impact oscillator, where we have a cushion behind the wall. In case of the hard impact, it's the instantaneous jump. In case of soft impact, it goes into the other side. And it has been observed that when the system grazes, there is an onset of a large amplitude chaotic oscillation. And this is somewhat universal in all grazing systems or impacting systems. Now, what happens after this may be a period 1 orbit or a period 2 orbit, but whatever. At the grazing condition, there is a large amplitude, narrow band of chaos. And that particular chaotic orbit has a specific structure, which most of you may have noticed. So that's what I'll be basically focusing on. The first shot on this problem was taken by Nordmark, who derived a first return map starting from a point, and it goes and hits the border, the velocity flips, and it comes back. So if we can find the x of t as a function of x0, then we are done. So that's what it did in this paper. So the flow is given by some function fx if the switching condition is not satisfied, or there is a restitution law followed when the switching condition is satisfied. And the switching condition is given as some function of x being 0, the h of x being 0. Now, a few definitions would be necessary. The normal velocity is the velocity at which the state approaches the switching surface, which is this. So it will be h derivative with respect to x times this function f. The normal acceleration will be the derivative of the v, and then it will be this. And the reset map, when it impacts the wall, is expressed as x plus some matrix times the v of x. So that's how he did it. So this w function is something that we'll talk about. And the grazing condition is where h is 0, velocity, normal velocity is 0, and the acceleration has to be positive. That's the condition for grazing. So what he actually argued is that if you have a Poincare section here, start from a point on the Poincare section, and then it goes and hits the border, flips, the velocity flips, and then goes back. But he argued that, as Rohit had just illustrated, you stop before it reaches. Because if you perturb it here, you have to stop at a point where none of the perturbations would hit the border. So you stop a point, then it reaches x2, and then go here, come back. So that the entire Poincare map will be a composition of 3 components. The first one for the flight from here to here. Second, the third component is the flight from here to there. And the second component is flight from here to here. And now he says that let's take a closer look at what happens in that middle part. You start from here, come here, go here, and go back. But then it takes some time to come from here to there and then jump here. You from here to go back, you evolve to the point x4, and then from here you go forward, so that what you need in the middle is a jump from x1 to x4. That is what we call the zero-time discontinuity map. And then we showed through a series of coordinate transformations and Taylor expansion truncated to the first order. So that he showed that the map actually becomes this. Notice the terms here. W is that W matrix evaluated at x star, the grazing point. Y is this quantity, which has, it is the amount by which the orbit would have gone into the switching surface. So it's negative value, so there's a negative here, so that it becomes positive. And it's a square root term. And so this is what, and this is the normal acceleration. Now, if you now compose the whole Poincare map, then you will have to put the first one, P, which is a linear map, simple. And then you have to compose with the zero-time discontinuity map. Then it takes this form. And then again, you compose with the next one, P2. Notice that this total map contains this square root term. And because of that, you have what is known as a square root singularity. To illustrate what it is, look at the first one-dimensional situation where there's a chunk to the left, which has a linear slope, but this one has a square root term here. And square root term, when you take a derivative, the square root comes to the denominator, so you have a infinity slope there. As a result, if you take a small interval here, it maps to an interval here, which is a finite length. But if you take a small interval here, it maps to an interval which is very large, and it was called as infinite local stretching, due to which you have this onset of chaos. That was the understanding. Well, now, whenever we have a two-dimensional system leading to a two-dimensional system, there is you can always take the Jacobian of the system before the impact and Jacobian system after the impact. So we were interested in understanding how the Jacobian evolves as it goes through the impact. So if you just do a coordinate transformation, you can convert the matrix into a form where you have the trace and the determinant are there. So effectively, the question boils down to how does the trace and the determinant evolve as you go through the impact. And we wanted to look at it from the actual system, experimenting. And as Marian has already said, he has built one such system, and we took advantage of that. And we are grateful to David for this. Well, he has already elaborately explained how it works. There's a shaker. This is the actual mass, and this is the wall. It's a screw that acts as a wall. And these are the leaf springs, so the whole thing goes up and down. So it can either not make a contact or make a contact, impaction. The whole thing is like this. But then what we wanted to do is to figure out how the Jacobian matrix changes as it goes from non-impacting state to impacting state. How do we do that? Basically, if it is in an equilibrium state, you have to quarter from the equilibrium and observe how it goes into the equilibrium region, right? As it goes to the equilibrium. In this system, how do we quarter? I sat with a pencil and his student James Inge. This is still there.
No, he left. Yeah.
He left. Yeah.
Exactly. Fate of agents. So yeah, you go.
Germany.
Okay, so many thanks. So I was sitting with the pencil, hitting quarterization, and then he would observe how it goes. So the results, I mean, I don't need to talk about all this because Marian already said this, how do we actually do the experiment. But the point was that when it is away from the grazing condition, it's easy to do the experiment. But when it's close to the grazing condition, it will do a tick. It can go from a non-impacting state to impacting state in 5 minutes. So for a whole day, we were ticking, and then we were collecting hundreds of data points. And after say a 100 perturbations, some 5 or 6 would pass the test. So it was a rather exacting experiment. But then the results were really wonderful. This coming from my experimental work is exceptional. You can see that nice spiraling inward orbit by these points. You can easily calculate it. Right? And we calculate the Jacobian, it came like that, but we were interested in the trace and the beam. And so when we observed that, we found that the determinant remains, this stays put. This result was for the system without pre-stressing, and this result was for the system with pre-stressing. In this case, the trace changes, but there's no abrupt jump at the grazing condition. But when there's pre-stressing, you see the clear signature of a square root singularity. Right? So the take-home message is that the determinant remains as it is, but the trace has a change, and it goes through like a square root singularity. So our focus, therefore, it's not that this result was a shot out of blue. We did anticipate, there was a theory for it, but we wanted to check on the actual system whether it does get that. Theories are always suspect, experiments. So then we needed to look at how the Jacobian behaves theoretically as you go from a non-impacting state to impacting state. Our grounding was in experiment, but our going forward from there. So as I said that this is the grazing orbit, this is the impacting orbit, and this is the non-impacting orbit. And in order to find it, you have to compose the total Jacobian out of the 3 components. And we know each of these, and therefore we can compose the Jacobians, right? And I've already shown the structure of the zero-time discontinuity map. When you take the derivative, the Jacobian comes to be this size, this shape. Let's take a look at what each component is. A star is a normal acceleration. W star is the W matrix of this. You recall, I said this is the distribution law. And this is the W matrix evaluated at the grazing point. Hx is the derivative of the H function, which is the function defining the wall as derivative with respect to x. And H mean is the extent to which the point would go into the wall if the wall were not there. So these are the terms there. So we need to evaluate each of these terms, substitute it here so that find out what actually this is. So first the boundary, discontinuity boundary, its expression is just position of the wall minus u is the position. So this equal to 0 is the equation. So if you now take a derivative, you get this as the matrix. The restitution is, as you make the impact, the position remains the same. U minus is the same as U plus, and therefore all that happens is this becoming the restitution law. W2 is a constant of restitution, so it is just a 1/2 matrix. So we now substitute. If we do substitute, we find that these two combine to make a square matrix. And when you compute the whole thing, then this whole term appears only here, which is just a term in there. And you immediately realize that the Jacobians aren't affected by this term, and this is where this square root singularity appears. So the square root singularity appears in just one term, and that has a particular position in this matrix, and because of that, it will not appear in the determinant expected. But so it will not appear in the determinant. That's it. But what happens to the trace? It will appear in the trace, right? It will appear in the trace. In order to figure out how it behaves in the trace, we had to calculate each component, as you understand that the components were how it flows, following a linear equation, jumps again following a linear equation. So we can always calculate these matrices. So because in the linear evolution, it will be the equation like this, and then you can always calculate this matrix here, which comes out to be like this. Don't look at all these forms, each and every term, you can always check later, that's not a problem. Point is that this is the form of that n. So you have got one chunk, jump, another chunk, n is known, this chunk is known, and in the middle is known, so we can just put together. So the Jacobian then becomes this whole term, this is the square root term, and this term multiplied. Bad algebra, but ultimately what comes out is nice because the trace becomes just a term without the square root singularity and separated from a term that has the square root singularity, right? That immediately tells us that if you can somehow make this term 0, then this term will have no effect, right? So if you have this term has no effect, so we have to see under what condition this term disappears. These are all known. You can put them together, and that leads to the conclusion that this is just sine omega naught t divided by omega naught, and then so this will always happen so long as omega naught is not equal to m times the forcing frequency divided by t. Therefore, that so long as this is true, then there will be a square root singularity, there will be an excursion to a large amplitude chaotic orbit, but the corollary is that if this condition is satisfied, then the singularity must vanish. Okay. That was a nice result. We were elated, but I never tried theoretical result unless you can test it. So we again told Maria, they need to test. A few there, and then we did the test. These are the numerical. So if you do not have a integer ratio, then you have this, but the moment you have the integer ratio, the ratio between the natural frequency and the applied frequency, it has to be an even integer ratio, then there's no excursion to the chaotic orbit. Does it really happen? It was really surprising result. Does it really physically happen? So we did the test on their rig. We found that when the m value, the ratio, is a non-integer number, then you have this something like this. So there is an excursion into a large amplitude chaotic orbit. But when you take the integer values, there's none. That was really nice. We are on the 70. When we come to the bar, we had nice evening. But then there's an issue. Notice the result that the ratio has to be the ratio has to be a perfect even piece. Generally, it will disappear. Otherwise, how can we make it perfect even integer experiment? It simply can't. But it still worked. So what happened? Then Professor Pablo Square took it up and we came in, they sat together, I came back to India, and they worked out that if you have for different values of the parameters, these were plotted with this projector, these lines are not visible. These are the integer lines, integer values of m. We found that somehow the blue is the part with the period 1 orbit. All through these lines, there's no other orbit. Now, I asked Mariam to say something that you know that you don't know. I'll now say something that I know that is true. I do not know why this is. But we have seen in that it happens that somehow there's a clear region around the integer values where the period 1 orbit remains period 1 as it goes through. The take-home message is that if you have a physical system in which the the excursion into a large amplitude oscillation is undesirable. You just set the frequency ratio at that time. That's it. It works. Now, the point is that all the time we see what is known as the narrow band of chaos. A very narrow band of chaos, but the Nord-Mach map, if you simulate it, you have something like this, which is not the same. Even though the Nord-Mach map does explain why the fixed point immediately becomes destabilized, so that things are repaired from there, but still it does not, it leads to sort of a slowly growing size of the object. Why that does not happen in physical way. What happens is this, why? Now, in tackling these kind of problems, okay, these are all experimental results. In all experiments, you find that at this point, you have a large amplitude chaotic orbit, and that normally has a fingered structure. You can see that. And you see, period 1 to period 1, but there is a large amplitude chaotic oscillation there. Why? Now, around this time, few years before we looked at this, we worked on another completely different thing. A group in Maryland, they observed something called dangerous border collision pattern. What's that? A situation where a fixed point remains stable as it goes to some event like a border collision bifurcation, remains stable, but the system destabilizes. Why? Because its basin of attraction shrinks to zero size. That is what they observed. They reported in PRL, and then we did some work to explain why it happens. Now, I had no physical example of such thing happening because they worked on the what is known as the normal form of the border collision bifurcation. That's sort of a model. But then I had a hunch that something like that might be happening in our system, in the impact oscillation. So what actually happens is that you have a stable fixed point with a basin of attraction, but the basin of attraction is created by, basin of attraction, the basin boundaries are always the stable manifolds of some unstable fixed point, right? So there's a period 3 saddle fixed point sitting there, but then that saddle shrinks, its distance shrinks and comes to this point, and then after bifurcation again it increases. So at this point, the size of the basin of attraction is 0. So even though looking at the eigenvalue, the fixed point remains a slight deviation from that will diverge. Now, in order to check whether something like this happens in our system or not, we had to find out these points. That means the unstable fixed points. So in our case, we had to detect unstable fixed points, and the usual programs did not work. Auto and other things that did not work. So we had to write our own programs to do it by neutron induction and then continue the orbit. And the result was this. Notice, this is the bifurcation diagram in which this is the main non-impacting orbit, and at this point it undergoes impact. While it is the non-impacting orbit, then in this state, coexisting with it are unstable periodic orbit, period 3 orbits, not 1 but 2. And if you follow them, we find that they all originate at this point, which is a situation where the main orbit has not undergone grazing. So it is nice and fine that wall is there and what is there. But still, at that point, the period 3 orbit, if it existed, it would have grazed. So that grazing causes 2 unstable saddle fixed points to come into existence. Normally, that doesn't happen in a physical system because you have only saddle node bifurcations. But in case of a non-smooth system, there is a possibility of having saddle bifurcation. That's what actually happens there. Now, as you change the parameter, they approach, but then look at it very close here, and this happens in a grazing bifurcation, this one. You can see the orbit actually grazes. This unstable periodic orbit grazes. look at this small neighborhood, you will find that these two orbits come and converge onto the main, the one that is going to impact at that point, that orbit, which is exactly the same as the situation of the dangerous water collision bifurcation. So what happens is that at this point, all nearby initial conditions are repelled from it. They go away. But immediate question is, where will they go? They cannot go to infinity, right? They will go. Here is a coexisting orbit, right? These points are coexisting. Therefore, there is a period 3 coexisting orbit, and it will have its unstable manifold. So it goes into the unstable manifold of that period 3 orbit that is coexisting. Check. The check would be if I can draw the unstable manifold and if I can draw the attractor, if they're identical, then that's my hypothesis true. And that's what happens. The first one is the unstable manifold, and this is the attractor. You see they're identical, which means that it goes to that. So this explains the finger structure that you often see. It is actually the structure of the unstable manifold of that period 0. So this is how we finally explain why there is a narrow band of chaos. Okay. Still the question remains, why didn't the Nordmark-Mack, which was a wonderful piece of work, fail to explain this band of chaos? We obtained the actual pointering map. That means starting on every point on the pointer surface, where does it go? And accordingly, we plotted it, and we found that the actual map has a shape like this. Notice that it is actually a 2-dimensional system, but a non-autonomous 2-dimensional system, this force. Therefore, time is also a variable. So if you take it that way, then you place the pointer section in one of them, the velocity and the time become two variables. And then the attractor is like this. It exists or extends into a region where the normal map is no longer valid. Normal map is valid in a small neighborhood of the grazing point. And it extends, size of the attractor is large, so that it extends to a range where it goes beyond that. That is why it doesn't work. That means the normal map fails to capture it. But then, as you say, that your plan is to extend the normal map, including the higher order terms. Go ahead, sir. Well, that's what might lead to a solution of this one. Okay. Yeah, and what else done? Because we started late, I was looking so that we can finish on time. The take-home message is that if in any application there is an the onset of a large amplitude chaotic behavior is undesirable. For example, Marianne was talking about Jeffcott rotor and things like that. So in those situations, definitely undesirable. If it's possible to set the frequency ratio at an even integer. That will do it. So it's not necessary to have a feedback control or anything like that. Just a parameter setting does job. The narrowband chaos is caused by a dangerous border collision bifurcation. And in such systems, what file information can be obtained by locating and continuing unstable periodic orbits. In many literature in this particular field, this attempt of locating and continuing unstable periodic orbits is not done. So I will emphasize that because it often reveals what is hidden. Because in our case, the grazing that happened in the period 3 orbit is completely invisible. You don't know. You don't see it. So it's invisible grazing, but we could figure it out only when we located the unstable periodic orbit continuum. And the normal map cannot capture the onset of large amplitude chaos at grazing because it is truly a global phenomenon. And normal map captures the local behavior. And it's a result of a lot of papers which I presented. Okay, thank you.